Pedro Castel from Brazil. And this is still chemical fields and diffusion. We will cover in this material. Don't remember, actually remember, workshop is live streamed, recorded, and distributed. So no weird things in camera so far. Okay, so we will cover interpretations of diffusion, diffusion across barriers, decay, the diffusion equation of decay, exponential field profile instead of the linear profile that I'm gonna talk in a bit, source and sink, and the diffusion equation with decay and sources. So continuing our previous lecture, this is very important for you guys to know if you are modeling, for example, a tissue that presents a kind of a linear field or chemotaxis. It's very important for you to know how to implement a linear field. So I will show in the code how to do it for you, and then we'll go back and do step by step together. Okay. So before, yeah, the cat definitely agrees. So let's jump to edit here. So do not do anything yet. I will show you how to do, and we build it together later. So let me just close these windows and start from a new project. So this will be, I don't know, linear field, which is constant gradient. Sometimes I will switch because I don't know. So 100 by 100 to make things run faster. So 256 will take a while. Again, these boundary.
Pedro, are you supposed to be screen sharing to edit?
Oh yeah, sure.
Yeah, it didn't switch.
Thank you. So I will share my entire screen. Are you seeing it now?
Yep, it's good now.
Okay. I set 100 by 100. Thank you, Hayden. Remember that these boundary conditions are for cells, not for fields, so it doesn't matter which one you set. Next, set a cell type, a generic cell type. Next, generic field, oxygen, diffusion solver, contact and volume, doesn't matter here for in case of fields. Next, finish. Okay, so in the XML, as I told you in the previous lecture, but I will revisit it, you receive these steppables diffusion solver FE with the name of the field. Here you have access to your global diffusion constant, your decay constant. This one I will comment out because it doesn't matter here. Then specifics for each cell type, I won't use it yet. Secretion, I won't use. And here are the boundary conditions. So I told you by default, you set periodic because these settings are a little bit messy. So yes, now we don't have any initial condition. So our initial condition is commented. And periodic boundary conditions. So this would be, the result will be 0 field everywhere. All right. We don't see, okay. And now I will build a linear field. So to build a linear field, what you can do is set constant value at the left end and constant value at the right end. So if you have two different constant values in different ends, in the steady state, you have a line between those two values, a constant line, because the diffusion behavior is to flatten things out. So if you have one value here, another one here, the most flat surface would be a plane, right? A straight line between the 2 points. So getting back to the slides, if you set two different concentrations, it doesn't matter the initial state. In the steady state, you get a line. So it doesn't matter the initial condition here. I will set a constant value of 0 in one end and one in the other. And the y-axis, as I only want the linear field in the x-axis, the y-axis doesn't matter, so I will leave it as periodic. Let me close this one and open in player. It's taking a while to open for some reason. Yeah, it opened here. Okay, so by default, you will see the self field. To see your field, just click this drop-down menu in the window, click your field oxygen, and run. You didn't comment out periodic in the X. Yeah, so if I didn't comment, yes, I didn't comment, so this is a huge problem. Yes, now it was conflicting, so I wasn't getting the right result, as Sharon pointed out. Thank you. And now I only have the constant value. Initially, you choose the field. So initially, where you mean? In the player here? Yes, I choose the field oxygen here. Yes, in the wizard, I choose the name. But I will go over each step again with you later, okay? So don't worry if you didn't follow a specific step, okay? Now I run again with the correction that Sharon suggested. And so what's happening? So in the left boundary, I have constant concentration 1, and in the right axis, I have constant concentration 0. So the field is diffusing from the left to the right boundary until it reaches the steady state where it's only a straight line. But it takes too long, right? So one thing we can do is increase the diffusion constant. If I increase the global diffusion constant to, let's say, 10, hopefully it's enough. We'll see that the field propagates faster, right? And in the steady state, we'll see that it reaches this flat plane, right? Where these isolines are evenly spaced. So you can see one isoline here. In my mouse, it's over the yellow part, so it's difficult to see. The other straight line here in the middle, and the last one in the right. One way to reach the steady state straight away is by setting the result as the initial condition. So in the case of a straight line, you just write a straight line as the initial condition. So in the case of a linear field from 1 to 0, what you can do is minus x. So it's this, it's a descending line. Then you divide by the total length of the x length of the lattice. And then you sum 1. So the line goes 1 unit up, and we have our result right away. So this is the resulting linear field without having to wait that time to diffuse, okay? So now we'll go over again, step by step with you. So please open your to edit. Open your tab to edit and begin a new project. For example, I'll go over this again, Venceslas. I'll go over this again, don't worry. But by default, no, by default, you put periodic by default. So whenever you're starting a new simulation, I recommend you uncomment periodic and comment out the rest of the lines. because the automatic input from to edit is can mask your simulation. So open your to edit and follow the steps here. So first step, I have to show in my to edit. So CC3D project, new project, give it a name. Pedro attempt, I don't know. Python plus XML, next. Here, choose lattice dimension 100 by 100. And that's all. For the general simulation properties, 100 by 100. Yes, I am trying to share my to edit. Is it sharing my to edit? Can you see it? Can you see it? Okay. All right, let's move on. So in cell specification, just put a cell, whatever. CompuCell needs a cell, so it prevents some bugs. Because sometimes it tries to find a cell, it's not defined, and it can crash. So put a cell, whatever. Okay. So next, here in chemical fields, give it a name, oxygen, I don't know, I don't care. Would be your name. Select your diffusion solver. There are plenty of options, but select diffusion solver FE. Then you hit add. So you see your field name and the diffusion solver in the list. All right. I know this window is very annoying. It pops up and you have to switch back, but that's the way to go, unfortunately. So, okay, next, cell properties and behaviors, contact and volume flex, doesn't matter either. Bothering you again? Okay. Next, finish. So there we have our simulation, and our next step is going to the steppables in the XML. In the XML, in the field steppables, so in the bottom of the file, you'll see your oxygen field or your whatever field that you chose, okay? And you will set the initial concentration, the linear field profile to initial concentration, which is minus 1/100 times x plus 1. And then in your boundary conditions, you set your x boundary conditions to constant value from 1 to 0. Okay, 1 in the left one, in the left boundary, which is the minimum. Your to edit didn't load the diffusion part. One thing you can do is load it yourself. So quick fix here for Julio. Julio, look here. CC3D ML plugins, no, sorry, steppables, and Diffusion Solver FE. Click that, and you will load your diffusion solver. Okay, so following the slides, what I want you to do is to come here, set your boundary from 1 to 0, and comment periodic. And the initial concentration expression, uncomment it, and set to minus 100x plus 1. This is the equation of our straight line. Let me try to do this. What is the difference between a plugin and a steppable? The difference is the implementation, how it's implemented within the compile structure. So I cannot explain it to you in terms of purpose, because some plugins are called every step, and some steppables are called only in the start. So there is no intuitive way to distinguish between them, at least for me. Yeah, for the user, it doesn't matter. Exactly. Okay, the steps in the steppables. I will do this more step by steppy. So I'll load the previous presentation, doesn't matter. For some reason, I lost my mouse in this presentation, but let's deal with it. Okay. Set both decays to 0. So the global decay constant to 0, and the decay coefficient to for cell to 0 as well. So let me minimize this one, put this one to the side. Okay, more step by step. 0 in the decay, and 0 in the decay here to the cell decay, the global decay and the cell decay. We're not putting periodic in the X, we are putting constant value left and right in the X. But what happens in the X dimension is independent of what happens in the Y dimension. So you can set periodic in both, you can set periodic in one and constant value in the other, you can set constant value in one, constant derivative in the other. So it really doesn't matter. They don't need to agree to each other, okay? Yes, I reached that. I reached the boundary once again. Okay, so then do this first. Set global decay constant and decay coefficient both to 0. Okay. And comment out the secretion line. So in line more or less 67, there is a secretion line. You can comment it or set to 0, doesn't matter. I will comment it. No, I will set to 0, whatever. So what I asked you to do is global decay constant to 0 and decay constant for cell to 0 and secretion to 0. All right. Next step, go to your boundary conditions. Sorry, go to your boundary conditions and set the X condition to 1 in the left and 0 in the right. Let me close this. Like I did here. 1 in the left, 0 in the right. And the initial concentration of -1/100, X plus 1. So this is the important step. Okay. And set your Y boundary conditions to periodic. So comment out lines 80 and 81 and uncomment line that's 83 that says periodic. So our Y coordinate must be periodic, okay? Secretion actually do here, what does secretion actually, it secretes. When the secretion value to non, it secretes, ends up with the cell. Yeah, we'll cover that later, okay? So let's not rush. X not thank you, Sharon. Yes, so yet again, I would commit the same mistake. Thank you. Okay. How are you with the exercise so far? Run the simulation and see that it gives the right pattern. So run it and see the linear gradients yourself. Did you get the gradient? Like this? Compensal crushed in for getting an error. If yours is 90 degrees flipped, Melanie, you probably set the opposite. So you set boundary conditions from 1 to 0 in the Y coordinate and periodic in the X. So the other way around, which is not a problem. And Serena and Goldsmay, invalid token. Yeah, that's a possible mistake. If you mistyped something in the XML, it's a problem. Yeah. What you can do is, yeah, invalid token probably is a invalid character in your XML. But what you can do is take the simulation ready in from the demos folder, okay? If you want to go back to the linear field, the constant gradient, I can help you with it in private later, okay? So that's not a problem since we had 2 people not being able to complete 3 actually. So the demo code you got, no, it's not cell division. What's happening, Serena? I'm confused. the demo code in the, so Hayden gave a link. I will send you the link again. Yes, both. Is in student materials, demo codes, and there's a folder called chemical fields and diffusion. Inside, you can grab the simulation. Okay, let's keep going. So for the field visualization, when you're visualizing your fields, you may face some problems like you lose your field completely, you don't see it anymore, or it's outside the range of the colors in the color bar. So what you can do is go to Tools, Configuration, the Field tab will have all the configurations you need. So you select your, go to the Field tab, and you can set, for example, the minimum and maximum value for that field bar. You can fix these values or unfix, so it will get the highest value on your simulation. You can set the ISO values, which will be those lines that I was showing you, either by the value of the lines you can set, or also the number of lines. And also don't forget that these configurations will apply only to the field you choose. So for example, here I'm choosing oxygen. If I had other fields like nutrient, etc., I would have to set one by one. So it's very important that you have some interpretations of the diffusion process in your minds. So for example, the very basic intuition, which the higher the diffusion is, the faster the diffusion takes place. Okay, so this is the most basic intuition. It helps you comparing different molecules diffusion behavior, and also compare the same molecule in different situations, in different media. So for example, oxygen in air diffuses completely differently from oxygen in water, which also diffuses completely different from oxygen in a tissue, right? So for example, if we take here oxygen in water, 1,800 micrometers squared per second, while oxygen in air is much higher, is 2 times 10 to the power 7, right? So it's completely different, the ratios, depending on the medium you are, and depending on the size of the molecule, for example. So G-actin is a protein, it's much larger than oxygen, so you would expect it to have a lower diffusion constant, okay? So this is the most basic intuition about the diffusion constant. So the higher is the diffusion constant, faster diffusion will take place. There is the geometrical interpretation, so it's a bit more mathy, but it's much more accurate than the previous one. The previous one, it's just an intuition. Here, we really can measure stuff and compare. In this case, the geometrical interpretation. So let's say you start with a distribution of a field and you watch it spreading over, over space. So the size of this distribution, the standard deviation of this distribution squared goes with time, goes linearly with time. So the variance goes with time, the standard deviation squared goes with time, or you can think, for example, that the size of the distribution grows with the square root of time, okay? So this geometrical interpretation can help you understanding the behavior of distribution of a field over time. And of course, there is the statistical mechanics interpretation. So let's say this blue particle is a protein inside the cytoplasm, which has water, other organelles, everything. So everything is colliding, and this molecule, this protein, I don't know what it is diffusing. So this random walk, this Langevin motion, it's describing, makes this molecule travel. So if you have a bunch of these molecules, they will diffuse as a consequence of this microscopic phenomenon. Okay, so in statistical mechanics, the interpretation is that the mean square displacement of particles changes linearly with time, the mean square displacement. And this, by the way, is the definition of the diffusion constant, which for single particles. So for single particles, you can measure a diffusion, which is the mean square displacement of the particle over 2 times the time interval. So in my opinion, it's good to have all these 3 interpretations in mind. But if I would choose one, I would choose the geometrical interpretation. In my opinion, is both intuitive and useful in practice, okay? So the size of the distribution grows with the square root of time. Now there's a demonstration that I wish to do with you, which is building a membrane in the middle of the simulation and see how the field diffuses through it. All right. So to build a membrane, let's see how. Yeah, and there is a plotting, but let's do the membrane here. To do the membrane, you must create the cells from Y0 to Y100 and from X40 something to 50 something, or from, I don't know, 50 to 60. So you create that thin layer of cells in the middle of the simulation and set for them a diffusion constant lower than the diffusion constant in the medium. So I will do it for you. You don't need to do it with together with me. It's not a guided exercise, it's a demonstration. So for now, just watch me doing it. Yeah, I will put the entire screen here to edit. I will build my layer of cells from, let's say, 45 to 55 in the X and 0 to 100 in the Y. So this is basically a thin layer of cells in the middle of the simulation from X 45 to 55, Y 0 to 100. Okay. I will set the width to 10. So I have one cell in top of one another. I will freeze the cells. So you can freeze your cells by typing freeze in your cell type plugin. So the type cell is frozen now. Okay, it won't move, it won't interact with anything. And I will set a diffusion coefficient for this specific cell type, lower than the global diffusion constant. So let's say, for example, for the global diffusion constant and 0.1 for the cell. And now I run it. Where is here? Okay. So first of all, oh, I think, yeah, it's the wrong simulation. I have to close this and open again. It's the wrong simulation. till the wrong simulation. I have to actively select this and open in player. Yes, there we go. To the freeze attribute, yes, you don't need to set any value to the freeze attribute because it's either frozen or not. There is no in between. It's either frozen or not frozen, okay? So this is my thin layer of cells in the middle of the simulation, as you can see in the cell field. And in the oxygen field, you can see that it has a different behavior inside. So it diffuses faster outside the membrane and slower inside the membrane. If you do the opposite, if you set a lower global diffusion concentration outside and a higher diffusion coefficient inside the membrane, the result will be the other way around. It will diffuse faster outside the membrane and slower inside the membrane. The demo in the demo folder has a graph plot of the concentration in the x direction, along the x-axis, so you can see how the field concentration breaks, which I'm showing here. So if you would plot the graph, you would see this plot here when the diffusion rate is, it's not a rate, sorry, it's when the diffusion constant is lower inside the membrane and higher outside. And it would be the other way around if you had a higher diffusion inside the membrane and lower outside. Yeah, so the difference is the ratio between the diffusion constant inside and outside the membrane. This is the diffusion inside the membrane. And this is the diffusion outside the membrane. Okay? The global diffusion constant is the diffusion everywhere. When we set the diffusion constant specifically for the cell type we want, it will overwrite the global diffusion constant in that particular space, in that particular position. So in all sites where we have the cell type cell, the diffusion coefficient is 10 instead of 0.1. So let's do James' suggestion. If trying to simulate the diffusion and glucose inside the vessel where cell type is A, where cell type A is, okay. Would I use a similar approach? Depends on how detailed you want to model the boundary between the vessel and the cell. But yes, you could use this approach. This is not a mandatory approach. This is a demonstration of how cells interact with the field. So let's do what James suggests. So James is suggesting us to open a hole inside the membrane. So let's say we are simulating a ion channel. So one way we can do it is divide our region in two regions. One region in the bottom, one region in the top, and a hole between them. So instead of creating the entire membrane from 0 to 100, we can create from 0 to 45, and another one from 55 to 100. As simple as that. So now this is our cell. Okay. and there's a hole inside. And now we can see what happens with the field. So the isolines help us. Oh, sorry, there's a problem. I have to set, it has to be a membrane hindering diffusion instead of the other way around. So the effect is clear. So the membrane is blocking diffusion, but there is a hole in the membrane. So what will happen? So the field can diffuse through the channel, and it diffuses much, much slower through the rest of the membrane where there is no channels. Yes, let's take a look at the frozen part again. So when you set your cell types here, you can set this attribute freeze like this. So I'll give to you in the chat. If you set this attribute freeze, it doesn't matter the contact energy, it doesn't matter the volume, the target volume, it doesn't matter target surface, doesn't matter anything. It will stay still like a barrier, like a wall. Yes, my simulation, I can leave my simulation running and it's already in steady state pretty much. So you can see that there is more flux of field through the ion channel than through the membrane. Yes, so the ion channel is basically an opening in my barrier. So I just created a new region. I could create more regions. So just for the sake of the example, as Tamayo is requesting. So basically what I did is I created one region from 0 to 45 and another region from 55 to 100. So there's an opening between them. From 45 to 55, there's an opening, right? So I should, so let's do, for example, from 0 to 20, from 30 to 60, and another region from C70 to 100. Let's see what happens. What would happen in this case, Tamayo? Look at my code and tell me what will happen now. Two ion channels, perfect. So let's run it. Yes, Vincenzo, yes. So you can create cells, initialize cells in the steppables. It is possible, yes. And we will cover that in the second week in the advanced CompuCell. Yeah, so there we go. Two ion channels, more or less. Two openings. We can see the openings here. Okay, let's move on. I would love to do everything step by step, but we have to move on. There are plenty of exercise if you need. So ideally, we would plot the concentration. but we saw how to plot. You can revisit the lectures on how to plot and implement it yourself, or you can get the code running with the plot from the demo code folder in the student's material. All right. Okay. Now let's cover decay. Decay is a very important concept because cells can take up nutrients. Cells can break up molecules. Molecules can deteriorate and disappear. So many processes can make molecules disappear in the simulation. In the simulation, in a biological situation, right? But decay is a much more general concept. Decay is often used in, for example, in radioactivity. For example, carbon-14 decays, and you can measure the date of something with the level of decay in the sample. Okay, and obviously in chemistry, synthesis of some molecules or absorption of some molecules can also lead to decay. So, for example, I have this graph here, the upper graph. We can see that molecule A, species A decays. We can also see that species B is synthesized but start decaying as well. So this is also a decaying behavior. And we can also see that species C does not decay. All right. There is a very basic mathematical equation for the decay, which is the rate at which something decays is proportional to the amount of field you have. So in the case of a radioactivity sample, for example, the more you have of this radioactive sample, more it will decay. And as you lose it, less it decays. So there's a proportionality between the ratio of the decay of the ratio of how much you lose your field in time to the amount of field you have. Okay. So probably I was not clear enough, but basically the rate at which something decays is proportional to itself. And you can solve this equation mathematically and derive the equilibration time or relaxation time, which is 1 over the decay constant. Okay, 1 over the decay constant is the time it takes for you to lose about 63% of the original value of the sample. It is related to the half-life. So the half-life is the time it takes for you to lose half the initial amount. The relaxation time is the time it takes for you to lose 63% of the original amount. You can couple it to the diffusion equation. And if you do that, the only thing it changes in the decay equation is that now it happens everywhere. So this equation means that the decay, which is gamma times C, is happening everywhere. Okay, and what you need to know about the decay is that gamma, this coefficient here, is the decay constant, and the higher the decay constant is, the faster your field will decay. So if there is no other extra mechanism responsible for increasing your field, for example, a source, the field will inevitably go to 0 everywhere in the steady state. So you will lose all your field as time goes on. Okay. In biology, you may find, for example, decay inside the tissue. So this is a paint masterpiece by me, where you have, for example, tumor cells in the corner here, and for example, a glucose field. The glucose molecules diffuse inside the tumor, and the tumor absorbs the glucose. So you will notice an exponential profile of the field as it penetrates the tumor. So what you expect in practice, if you plot the concentration as a function of the distance from the surface of the tumor, is an exponential decay in space. Yes, Lampers, you can, yes. So having this exponential profile, you can derive it mathematically as well. The length, the typical length of this exponential profile is the square root of the diffusion constant over the decay constant. So this is very important to have in mind. So for example, this can be measured in an experiment. So you have your experimentalists helping you with your simulation. They will probably give you the exponential profile of that concentration in the tumor, and you can derive your constants, for example, the diffusion and the gamma constants. So this is a real measurement, a real experiment in a tumor where they measure the concentration of oxygen as you get inside the tumor. So left of the zero line, which is the dashed line, it's the concentration of oxygen outside the tumor. And as you get inside the tumor, the concentration of oxygen decays, which leads to that exponential profile. All right. So let's build the exponential field. As an exercise for us. Build an exponential field in CC3D using decay and boundary conditions. Plot the concentration across the relevant coordinate. I will do it for you, and you watch, and then I go over it again, and you will follow me, okay? So I will take advantage of this simulation. Don't bother with the diffusion coefficient in that cell specifically, and set, for example, 0.01 global decay constant. Is that what it says? Global decay constant 10 to the minus 3, which means 0.001. And constant value 1 in the left, 0 on the right, which is already set in my case. So 1 on the left, 0 on the right. Why boundaries to periodic? And that's all. That's all we need to do. So let's run it. Select oxygen. So it started linearly, and now it's getting to a new shape, which is an exponential shape. Okay, so if I was plotting the concentration across the x dimension, I will see the exponential profile. But I can make it more dramatic, increasing the global decay constant. So if I make it 0.01, it will have a more dramatic behavior here, okay? So this is useful, for example, if you're studying chemotaxis, how the cell responds to a linear gradient is different from how the cell responds to an exponential gradient, and the exponential gradient is more easily found in nature rather than the linear. Okay, so let's code it. Take your simulation you already had with the linear gradient, and what you are going to do is basically set a global decay constant, a positive global decay constant, and that's basically it. Okay. So I'll go back to the slide here. Set a global decay constant. This is my code. And you can play with the decay constant to see the exponential profile better if you want. All right, so let's move on. Now let's talk about sources and sinks. Source is, I still have a solution only. Ah, okay, no problem. So the source is basically a constant influx of field in the space, all right? So let's say you have your uranium decaying, and someone is putting more and more uranium inside the box, let's say. So it keeps decaying, and someone is adding more and more uranium, and this goes on. All right. So it's a constant influx of field happening everywhere. Right. So in this formulation, S is a constant rate of field variation in time, and it's happening everywhere. And the sink is the same, but the opposite sign. So if something is sinking, you are losing at a constant rate. But unlike decay, this is not a decay, by the way. This is very different from a decay. A sink is not proportional to the value of the field at the specific location. Okay, so the sink is a constant rate. So for example, if you have zero field, you keep losing field. So you reach negative values, which sometimes doesn't make sense, right? So if you're talking about oxygen concentration, there's no such thing as a negative oxygen concentration. So this is not the proper way to model many behaviors using the sink, okay? So this you must be careful about. But as a source, you can use source to model, for example, secretion. If you put both a source and a decay together in the same system, so let me give you an example. The muscle produces a toxin and absorbs the same toxin, okay? But it releases the toxin at a constant rate, and it reabsorbs the same toxin at with a decay constant, which means proportional to the concentration of this field. So in this type of system, the concentration of the system reaches a maximum, okay? Or if it starts above the maximum, it will reach this maximum concentration, which can be calculated, can be derived mathematically, which is S over C, the source ratio, the source rate, sorry, over the decay coefficient. Yes, Julio. Yes, you can create a flux adding a source and a sink. Yes. Perfect. Keep in mind that this relation may not work. For example, if your source is in a different location than your decay, right? So if they are in different positions, different locations, this relation will not be obeyed by your field. Yeah, so in this case, as source is everywhere and decay is everywhere, this relation holds. But if you have your source at a particular location and your decay at other location, this relation will not hold. So although in this equation that I am using as an example, both source and decay are happening everywhere, you can specify a location for them to occur. So in this case, they will not be just a constant S or gamma. They would be a function. They would be a field as well by their own. They will be something that depends on the space, and sometimes depends on time as well. Okay. So if you specify for at specific locations, this relation here will not hold. So there's a demonstration we can do about decay and source, which is creating a tissue, setting a secretion in the tissue, and a decay. Yeah, so let me show you here. I don't know if you are familiarized to these equations, but the sink is minus S. Okay, this is a source. If you invert the sign, if you put a minus here, this is a sink. Okay. And we have the decay here. The decay is minus a constant times the concentration field. So the sink is a constant rate, and the decay is proportional to the intensity of the field. These are the differences. Okay, so if you have a high intensity of field, it will decay more than if you have a low intensity field. In the case of sink, it doesn't matter the amount of field you have. It will always sink at the same rate. So let's think of an example. You are driving a car. The rate at which you lose fuel is not proportional to the amount of fuel you have in your car. So this is a sink. You will model this as a sink. Okay. Now let's say you are building, for example, a reaction, an explosion, for example. So the amount, the rate at which you lose your chemical species in the explosion is proportional to the amount of chemicals you have in the first place. If you have a low concentration amount of explosive, it will explode slower than if you have a high concentration of explosives. So these are the differences. Or radioactive decay, or pandemics, the rate at which you lose people. Yeah, okay. So I will demonstrate in practice this ratio. So I will start with a region of cells, let's say from 20 to 80, a square of cells, like I was showing the slides. Okay, also frozen, doesn't matter. I will start with 0 initial concentration, and I will make them secrete oxygen. They will secrete oxygen. This is very strange. but they are secreting oxygen at a 0.1 rate. Okay, and at the same time, I will set a decay for oxygen inside the cell at the same time. Okay, so 0.1 decay inside the cell. By this relation here, S over C, by this relation, what you expect? Well, if the decay constant is 0.1 and the secretion is 0.1, inside the cells, you expect a maximum concentration of 1. So let's run and see. And I also have to change here, instead of periodic, instead of constant value, I will set periodic, otherwise it will mess up everything. Yeah, it will not mess up, but it's not exactly the result I'm showing the slide. If I run this, so see that I have both decay and source inside the tissue. All right, I have both decay and source in the tissue. So in the tissue, you can see that the value holds at 1 mostly. Okay, so if I change the visualization, it will be more clear for us all. Instead of freeing everything, I will set from 0 to 1. Yeah, so eventually, yeah, the field maintains at 1. Yeah, at medium, nothing's happening, so it will go to 1 as well. So to make things more interesting, I can set a high decay outside. Let's say 1 decay everywhere except inside the cell. Then we can see how the tissue holds this concentration of 1 inside, and outside it goes to 0 because outside the relation is not obeyed. All right. So as you go further from the medium, you can see that the relation tries to hold. So the decay outside is too high, but as you go into the tissue, the concentration reaches 1. If I set a lower concentration, this will be better for the sake of the demonstration. Yes. Inside the tissue, further away from the boundaries, concentration tries to be 1 because it's secreting at 0.1 rate and absorbing with decay 0.1. So the ratio 0.1 over 0.1 is 1, which is red here in our case. All right, so let's move on. Oh, yeah, so this is module 3.2.
And then if anybody has any lingering questions for Pedro before we take our break,
Yes, please take this time to.
There is one in the chat already from Melanie. Pedro, if you want to take a look.
Yeah, so the diffusion length. No, the diffusion length is the square root of the diffusion over the decay, as I put here. If you want to understand why that is, well, you have to actually, there are 2 ways of understanding this. One way is, in my opinion, is not convincing, which is basically, if you divide the diffusion by the decay, you will get meters square. If you take the square root, you'll get meters. No. The numerical interpretation is the numerical interpretation is how far you must go to lose your field by 63%. So it's like a half-life, but in terms of space. So let's say you are walking inside the tumor. So follow me with this graph here. So this is an experimental graph, experimental result. As you walk inside the tumor from this dashed line to the right, your concentration decays. So when it reaches 37%, which is, for example, here, this point here probably would be your diffusion length. So in this case, would be 100 micrometers for oxygen inside the tumor. 100 micrometers is your diffusion length. Okay. I'm happy to help. If you have any more questions, please feel free to ask them. If you don't have anything to do, please fill out the questionnaire. It's very important for us.